Hi everyone, hope you're well. And I'm really excited to finally be able to share this video with you that I've been working for almost a year. So to continue my quest to make the uncollapsible paraglider, I need to learn even more about the lines. So I want to go from 2 sensors to sensors on all of the lines. Practically though, that would be quite difficult. So I thought I would tackle one side so I can get away with just having 10 or 12 sensors and assume that in steady state in flight, both sides are going to be roughly the same. And the reason for doing this is to be able to measure the tension on each line in flight so that when we are at different brake inputs and different canopy attitudes, we can see what the tensions do, but also if we go through turbulence, what is happening to the tension on the lines. So this is going to be my most ambitious project yet, so grab a drink, get comfortable, and let's go together on this journey. So the requirements for this version is I want to have 10 or more sensors. The processor has to be fast enough to be able to keep up with them. I want it all integrated and robust, record all the data to an SD card and maybe display it on the screen, and good connections from the sensors to the main box because there's going to be a lot of them. From there I made a simple schematic of the main components and also tested them on the bench to make sure they all work with each other before committing to doing anything else. Oh, and I also designed my own sensors. So the next and trickiest step would be to create my own PCB to house all of these components. I started by building a schematic. This is just a way to show what pins on what components are connected to other pins. And then from here, if you convert it onto a PCB, you get something like this, which is more like the physical representation. So this is where you're actually going to have to physically place them somewhere and make sure that things are going to fit. And then after many hours spent doing this routing, you'll end up with something like this, where I've placed all of my components, I have mounting holes for everything, and we have our traces in our ground plane and our VCC plane. You can also add a silk layer, so this is in yellow is what is actually going to be written on the board, and you have to, it's a 2-sided board, so you have the top side and also the bottom side, which now shows flipped, and that's fine. As this was my first ever PCB design, I double checked and triple checked everything. I even 3D printed a little template to make sure all the holes aligned, and then crossed my fingers and ordered them. And then COVID hit, so it took a little while, but they finally arrived. So I'm going to be quiet for a bit, let you enjoy the PCB-ness and the soldering it all together. For the rigging, I've done a 3D model of the risers, lines, and all of the components that I need on it. And it was actually a little bit tight to package, so we had to come up with some solutions, as well as building some spacers for the opposite side that is not measured. The Ozone guys helped me figure out the rigging stuff and even sent me some custom made links so that I could have the non-measured side spaced out the correct amount, and also on the sensors having a backup line so that if the sensor fails, I won't just fall out of the sky. Then with all the sensors done, it was time to actually install it on the wing. And we chose Gemma's old Ion 2 because it's a glider we know very well and has actually less lines than modern gliders. So it was a little bit easier to rig up. So I did the spaced out side and I did the sensor side, making sure I tidied all the cables away because it was already going to be a bit messy, so I don't want to create any tangle hazards because this thing actually has to fly as well as measure. So that's all of the lines done. I had to remember to also extend the brakes, otherwise I would always have brake on, and install Tensi on my cockpit, so we're all ready to test. The clipping in process is a little bit more complicated than normal because you have to make extra sure that everything's untangled, connect everything, and then connect up to 13 sensors to your cockpit. So all that was done, initialized the scales and calibrated them, so ready for takeoff. Okay, gonna do 1, 2, 3. 1, 2, 3 on A1. I really wanted to test it out, but the wind on this day was very light and very low cloud, but after ground handling it a little bit, just managed to get off, and as the wind was so light I couldn't really stay up. So I just kept it flying straight for as long as possible to let it settle and have some good initial values for trim speed, and then hooked in a couple of turns and landed. I'm so happy. So many months working on this and it finally has worked. It was very interesting to see in flight because we have the display. I could see like 15 kilos on the main A, 11 kilos on the second A, and then kind of the more further away from the center you get and the more further back along the chord you get, the less and less tension you get. So it's, yeah, really interesting, and I think let's go back and see the results. So the raw data as it comes out of Tensi is just a text file with a line every 10th of a second, and it gives us the values for all the cells. So that's not super useful as it is, but we can plot that data as well. So this is that first flight. You can see here where I've pulled 3 times on the ace just to have something to sync, and then you can see the various phases of flight. Here's where I took off, and then this is kind of the steady state flight, turned left and right, a bit more straight flight, and then landed. In terms of line tensions, this is A1, A2, B1, B2, Stabilo line, C1, C2, and the brakes. So you can actually see on the brake traces when I'm not putting any brake on and how the brake input is put. Also, at first glance, I found it strange that the tension on all of the lines varies so much, between 13 kilos and 16 kilos on A1, for instance, when we're still in, straight and level flight. And then I realized that's because of the pendulum effect, and that's something I've noticed even when bench testing. If the weight that you put on the scale is even ever so slightly moving left to right, the scales will pick it up. So what I did is, instead of looking at that, I looked at relative tension rather than absolute tension. So this is, I call this G adjusted tension. So what I did is, for every set of values, I calculated the total tension and then expressed each sensor as a percentage of that total tension. So when it's steady flight, things don't fluctuate too much. And when you make maneuvers, there's a redistribution of the tensions. Specifically, when you pull the brake, you're putting more tension on the back of the wing and not so much on the front of the wing. And then, yeah, things get complicated when you flare to land. So with these quite promising results, it was time to test some more maneuvers. Wind's a little bit strong, so I think I might be able to get some more data this time. So for the second flight, I ended up doing some more runs at trim speed, and they correlated really well to the ones on the first flight. And I've also done some runs of minimum sync, so just a little bit of brake and at different amounts of speed bar. And the results are quite interesting. So using our trim speed distribution as our benchmark to compare against, when we have minimum sync, and that's about 3 kilos on the brakes, it does shift the weight backwards a lot. So tension comes off the A's and B's. The B2 and Stabilo stay the same, but C1 and C2 get a big increase, almost 100% more than what they normally have. For the most part, it looks like when we increase the speed bar, pretty much all the lines react linearly. It looks like the tensions stay roughly the same. There isn't a huge change, except for the Stabilo. It really increases the tension on the Stabilo and a little bit on A2, and it takes away from most other places. I won't go through anymore because there's a lot to unpack here. All the raw data, processed data, IGC file, time-coded video file, and with the animation, everything is available to download on our website. So if you're interested, you can download it yourself or share it with someone that you think would be interested in it. All the links are in the description. One last thing that I thought was quite interesting to look at is turbulence. I went through the wake of a tandem that went in front of me, and it was quite interesting to see that it got picked up really well. The red is A1, where it had the biggest dip, and in black you can see my brake input. I actually look at the timings on these, and from the big drop to the peak input, it was actually quite fast. In fact, I started applying brake even before it fully dropped. So that means that this rise in tension was what I felt before I knew that a big drop was coming. So really cool to see the dynamic aspects of it. So that's it. This was a really ambitious project. I'm super happy with the results. It took a long time, and I've learned a lot of stuff that I'd never done before. So that was really cool. As always, I want to say a big thank you to all of these lovely people that support us. If you enjoy these projects, consider supporting us on Patreon or YouTube memberships right underneath. And for this project, I want to say a huge thank you to Ozone, Matt and Russ and Fred that have really helped us figure out some of the finer details and use their expertise to push the project forward. So thank you guys. Don't forget to subscribe if you haven't already, and we'll see you on the next one. Bye.